Today we are going to learn about auto-scaling in Kubernetes, best practices. You will discover how to configure auto-scaling for optimized performance and cost efficiency in Kubernetes environments. Welcome to our video on auto-scaling in Kubernetes. Auto-scaling is a critical feature that allows your Kubernetes environment to automatically adjust the number of running pods based on the current load. This ensures that your application can handle varying levels of demand without manual intervention. In this video, we will explore the mechanisms behind auto-scaling, its importance in modern containerized applications, and how it can help optimize resources, maintain performance, and reduce operational costs. By understanding and implementing these best practices, you can ensure that your applications are both robust and scalable. In Kubernetes, auto-scaling is primarily achieved through three components: the Horizontal Pod Autoscaler, HPA, the Vertical Pod Autoscaler, VPA, and the Cluster Autoscaler. Each of these plays a unique role in maintaining application performance. Horizontal scaling, managed by HPA, increases or decreases the number of pod replicas. It is beneficial when you need to handle fluctuating workloads. Vertical scaling, handled by VPA, adjusts the resource requests and limits for your pods. This is useful when an application needs more CPU or memory resources. Finally, the Cluster Autoscaler ensures that your node pool can meet the demands of scaled pods by adding or removing nodes as necessary. Metrics are crucial here as they provide the data necessary for making informed scaling decisions. However, integrating these components can be challenging due to the complexity of Kubernetes environments. Solutions often involve using advanced metrics and tools to accurately predict and adjust to resource needs, ensuring efficient scaling.
The Horizontal Pod Autoscaler, HPA, is a vital tool for managing the number of pod replicas in a Kubernetes cluster. Configuring HPA begins with defining the metrics it will use to make scaling decisions, typically CPU and memory utilization. You should set a target utilization percentage, which acts as a threshold for when scaling actions are triggered. For example, if CPU usage consistently exceeds 70%, HPA will automatically increase the number of pods to handle the load. Best practices for HPA include regularly monitoring your application's performance metrics to adjust the target utilization as needed, ensuring that your application scales efficiently without over-provisioning resources. It's also essential to consider the cooldown period between scaling actions to prevent rapid fluctuations in pod numbers. Common pitfalls include setting the target utilization too low, leading to unnecessary scaling actions, and not accounting for the time it takes for new pods to start up. Addressing these issues requires a thorough understanding of your application's behavior and resource needs. While CPU and memory are the default metrics used by HPA, advanced configurations can leverage custom metrics for more granular control. Custom metrics provide insights specific to your application, such as request count, queue length, or even application-specific metrics like error rates. To integrate custom metrics, you can use Prometheus, a popular monitoring tool that collects and queries these metrics. With Prometheus, you can set up the Kubernetes metrics server to expose these metrics to HPA. Configuring external metrics involves setting up a metrics adapter that communicates between Prometheus and the HPA. The benefits of using advanced metrics include more precise scaling decisions, as they reflect the actual performance and demands of your application. For example, if your application experiences high traffic but low CPU utilization, a custom metric such as request count can trigger scaling before CPU becomes a bottleneck. Implementing these advanced metrics requires an understanding of both Kubernetes and your application's specific needs, but the payoff is a more responsive and efficient scaling strategy.
The Cluster Autoscaler is responsible for managing the number of nodes in your Kubernetes cluster. It adds nodes when there are pending pods that can't be scheduled due to resource constraints and removes nodes when they are underutilized. Implementing the Cluster Autoscaler involves configuring it to work with your cloud provider, such as AWS, GCP, or Azure, which provides the infrastructure for dynamic node provisioning. Node scaling strategies should consider factors like node size, cost, and the specific needs of your workloads. The primary benefit of the Cluster Autoscaler is its ability to optimize both performance and cost by ensuring that your cluster has just enough resources to meet demand without unnecessary over-provisioning. However, integrating the Cluster Autoscaler requires careful configuration to align with your scaling policies and cloud providers' capabilities. Troubleshooting involves monitoring node utilization and ensuring that scaling actions are appropriate and timely. Optimizing the Cluster Autoscaler can lead to significant cost savings and improved cluster performance. Resource requests and limits are essential concepts in Kubernetes resource management. A resource request specifies the minimum resources a pod needs to run, which affects how the Kubernetes scheduler places pods on nodes. Resource limits define the maximum resources a pod can consume, preventing it from monopolizing node resources. Balancing these requests and limits is crucial for optimal scheduling and performance. If requests are set too low, your pods might struggle to perform under load. If set too high, you risk underutilizing resources. Best practices for managing resource requests and limits include understanding your application's resource consumption patterns and regularly reviewing and adjusting these settings based on monitoring data. This ensures that your application has the necessary resources to perform efficiently without waste. Proper configuration of resource requests and limits can significantly influence the effectiveness of auto-scaling, as they determine how resources are allocated and used across your cluster.
Load balancing is a critical component of managing application performance in a Kubernetes environment. Effective load balancing strategies distribute network traffic across multiple pods, ensuring no single pod is overwhelmed. Ingress controllers play a vital role in routing external traffic to the appropriate services within your cluster. Integrating load balancers with auto-scaling involves configuring them to work in tandem, ensuring that as your application scales, the traffic is efficiently distributed across the new pods. The impact on application performance can be significant, as effective load balancing reduces latency and prevents bottlenecks. Monitoring load balancers and making necessary adjustments is essential to maintain optimal performance. This includes analyzing traffic patterns and scaling events to ensure that your load balancers are configured to handle current and future demands. By synchronizing load balancing with auto-scaling, you can achieve a harmonious balance that enhances both the performance and reliability of your applications.
Optimizing both cost and performance is a primary goal when implementing auto-scaling strategies in Kubernetes. Cost optimization techniques include using spot instances or preemptible VMs, which offer significant savings by utilizing spare capacity at lower prices. However, these come with the trade-off of potential interruptions, which must be managed carefully. Performance tuning involves adjusting scaling parameters, such as target utilization and cooldown periods, to ensure efficient scaling without unnecessary resource allocation. Analyzing the cost versus performance trade-offs is crucial, as over-optimizing for either can lead to suboptimal outcomes. Regular monitoring and reporting provide insights into resource usage and scaling efficiency, enabling informed decisions that balance cost and performance effectively. By implementing these strategies, organizations can achieve a scalable, cost-effective Kubernetes environment that meets their performance needs. Exploring real-world use cases provides valuable insights into the practical application of Kubernetes auto scaling. Case studies of successful implementations highlight how organizations have tackled challenges such as fluctuating workloads, resource optimization, and cost management. Common challenges encountered include misconfigured scaling policies, insufficient monitoring, and unexpected application behavior under load. Lessons learned from industry experts emphasize the importance of continuous monitoring, regular adjustments to scaling parameters, and the need for a robust testing environment to simulate different load scenarios. Strategies for continuous improvement involve adopting a data-driven approach, leveraging advanced metrics, and implementing automated solutions to respond to scaling needs dynamically. As organizations adapt to evolving demands, their auto-scaling strategies must also evolve, ensuring they remain aligned with business goals and technological advancements. By learning from real-world experiences, organizations can refine their auto-scaling practices to achieve better outcomes in their Kubernetes environments.
As we conclude this video, let's recap the key concepts we've covered. We've explored the mechanisms of auto-scaling in Kubernetes, focusing on configuring the Horizontal Pod Autoscaler, leveraging advanced metrics, and implementing the Cluster Autoscaler. We discussed the importance of understanding resource requests and limits, balancing load with auto-scaling, and optimizing cost and performance. Continuous learning and adaptation are crucial, as the landscape of Kubernetes scaling continues to evolve. We encourage you to implement the best practices discussed and explore additional resources to deepen your understanding. As you apply these concepts, you'll be better equipped to create robust and scalable applications in your Kubernetes environments. Thank you for joining us, and we look forward to seeing you in future videos.